Welcome student, this is video lecture 3 CH4501 unit 1 wave mechanics. I am Dr. Devang R. Pandya, Department of Chemistry, St. Xavier's College Autonomous, Ahmedabad. Well friends, in previous lecture we have discussed about quantum mechanical postulates and how to set up different quantum mechanical operators and related theories and their theorems. Today we are going to discuss regarding eigenfunction and eigenvalue. This is the definition of eigenfunction, eigenvalue equation. If an operator A operate on a well-behaved, when I said well-behaved, means a wave function must be finite, a wave function must be continuous and a single valued. That kind of wave function is called normalized well-behaved wave. So if an operator operate on a normalized well-behaved wave function to give the same function with a constant, then that constant is called the eigenvalue of that operator and the function is called eigenfunction, and the relation of this equation is known as eigenvalue equation. I have an example for that. Suppose I have operator A operate on a well-behaved wave function psi. It gives the same function psi with a constant lambda. Then this lambda constant is known as eigenvalue, and the function is known as eigenfunction. Some example to explain the eigenfunction eigenvalue equation. If a function f, that is exponential minus ax, is acted upon by the operator d by dx, the result is d by dx exponential minus ax is equal to minus a into exponential minus ax. So here this is the function, this is the operator. When operator operate on the function, gives the same function with a constant value, then this constant value is known as eigenvalue and this function is known as eigenfunction. So here minus a is considered as eigenvalue and exponential minus ax is the eigenfunction of the operator d by dx, that is a single differentiation operator. Second example, so that sine 2x is not an eigenfunction of a single differentiation, that is d by dx, but it is the eigenfunction of d square by dx square, that is double differentiation. So what will be the eigenvalue for this? So we need to prove three things here. When operator d by dx, that is a single differentiation, operate on a function that is sine 2x, you can see that we will going to get 2 cos 2x. Sine 2x on single differentiation converted into cos 2x with 2. So here function get changed. That means there is no eigenfunction eigenvalue kind of relation when d by dx, that is a single differentiation, operate on sine 2x. But suppose we have a double differentiation operate on sine 2x, we're going to get the same sine 2x function with a constant minus 4. So double differentiation gives the same function. So here double differentiation and the function have eigenfunction eigenvalue kind of relation, and we're going to get minus 4, that is the eigenvalue, and sine 2x is eigenfunction for operator d square by dx square. That is the way you can read this out. Now eigenfunction eigenvalue, some more example. So that if psi is an eigenfunction for linear operator A with eigenvalue lambda, then C lambda, where C is the arbitrary constant or a random constant, is also eigenfunction of operator A with the same eigenvalue. So we need to prove that if operator A operate on any function psi, will going to gives us eigenfunction kind of relation, and its eigenvalue would be lambda. And if we have C into psi, where C would be the arbitrary or random constant, then when operator A operate on C psi, that is a constant with a function, will give the same kind of eigenvalue, that is lambda, that we need to prove here. So this is the solution. Operator A operate on function psi gives lambda psi. So function remains similar and lambda is the constant, that is eigenvalue. But since A is the linear operator, so linear operator is kind of operator which going to operate on the same function, gives the same function with a constant value. And here you can see that when operator A operate on a function with constant, arbitrary constant C, so we're going to get a constant which is not get operated, so it remain outside. A operate on psi, and A operate on psi gives lambda psi. So if we substitute that value here, we get C lambda psi. Now lambda, that is a constant as well, so if we keep outside, we're going to get C psi. It means that operator A operate on C psi gives the same eigenvalue over here. So that is proved uh, with this statement. Now next theory that we need to focus is significance means, that is also asked as the average value, or it would be asked in the exam as expectation value of eigenfunction. The wave function psi is a state function which contains all the information about the properties of the system from the wave function or wave equation A psi I is equal to A psi I. So when I say state function, it gives all the information about the property. Means what? Wave function, as you know, associated with the probability of finding electron. So the position of that particle in space, the position of particle in respect with the nucleus, its kinetic energy, its momentum, its total energy, these are called different properties associated with that particle. And state function means it defines these information about the properties of the particle or properties associated with the particle, like position, position in space, position in respect with nucleus, kinetic energy, potential energy, and total energy of the particle. So when here operator A operate on psi I gives the same function psi I with constant A. Here also eigenfunction eigenvalue kind of relation, but here function psi is considered to be a state function as it gives all the information regarding the properties of the system. The provided the state function psi is eigenfunction, that we found here psi I is a eigenfunction of operator A. When a quantity associated with the operator A does not have finite value in a given state psi, the following procedure can be used. What is the procedure? Let's see. It has been seen that the absolute square of the wave function is a measure of the probability of finding a particle within a certain distance element, that is dx. That means some distance on the x-axis, that is the displacement distance on x-axis, that is known as dx, and its value is given by psi star x. Psi star is the complex conjugate of the wave function on x component psi x dx. If a large number of measurements are made corresponding to the different position, will be mean of the sum integral of the probability of all positions. This average value is also known as the expectation value. In this expectation value, we can get different type of uh, information regarding the position, momentum, and kinetic energy of the particle within the system. Mathematically, it is represented by this bracket symbol. Thus, the average value of position of a particle when particle is in the atom, position in space can be represented. Suppose on x component or x direction, so it is the average value represented in this bracket x, and that is indicated as integration psi star operator x, that is a position operator, psi dx, so that is the distance on x direction. In general, the expectation value or average value of a physical property A for a system whose state function is psi is given by this is the arrow to indicate the significance, means or average value or expectation value, integration minus infinite to plus infinite psi star a psi d tau. Now here d tau indicate dx, dy, dz. That means displacement of particle on x-axis, y-axis and z-axis, where a is the operator corresponding to the physical property, and that physical property means position, position from nucleus, position in space, kinetic energy, potential energy, total energy of the particle within the atom. This formula holds only if the wave function is normalized. Now, when the wave function would be normalized? When the wave function will follow all four conditions, then that wave function is considered as normalized wave function. Like psi must be finite, psi must be continuous, psi have single valued from minus infinite to plus infinite. Probability of finding electron is always 100%. If the function follow all these four conditions, it is called a normalized wave function. Otherwise, the following formula is used, that is A is equal to integration minus infinite to plus infinite psi star a psi d tau upon integration minus infinite to plus infinite psi star d tau, where psi is the wave function, psi star is its complex conjugate, e is the operator, and d tau is the displacement distance on x, y, and z directions. However, if psi is an eigenfunction satisfying this equation, a psi is equal to lambda psi, we shall find average value, that is significance means or expectation value for this eigenfunction as a, that is the eigenvalue. The average value will be equal to the eigenvalue corresponding to every observation. Now the average momentum, and momentum can be represented as px, and average, that means we need to represent into this box, that is called average or expectation value for the momentum operator of a particle described by a function psi is the expectation value or significance means or average value for the momentum operator. So in one dimension, this becomes px, that means on only x component, integration minus infinite to plus infinite psi star x, because it is x component, that is complex conjugate of wave function for x component psi star x, px, that is a momentum operator, psi x dx. Now displacement is only on x component because we have momentum of x component only. So that value would be integration minus infinite to plus infinite psi star x. Now we need to put the value for the momentum operator, which we have learned in a previous class how to set up quantum mechanical operator for momentum. So here the value of quantum mechanical operator for momentum on x-axis, that is h upon 2 pi I d by dx psi x dx. So this will going to gives us average value for the momentum of a particle. Now h upon 2 pi is constant, so we kept it outside the integration and we get h upon 2 pi I integration minus infinite to plus infinite psi star x d by dx, that is the operator psi x dx. Similarly, average energy of a particle can be written as, so we need to put the energy into this box to give significance means of energy or average value of energy or expectation value of energy. That is represented as integration minus infinite to plus infinite psi star x h hat. H hat means Hamiltonian operator psi x d tau. Now this is on three component x, y and z. That's why displacement is written as d tau. Now we can put the value of Hamiltonian operator over here. We're going to get integration minus infinite to plus infinite psi star minus h square upon 8 pi square m delta square, that is a Laplacian operator, plus v potential energy psi d tau. So this is the average value for the total energy associated with the particle confined into an atom, or this is the value of significance means or average value of energy, total energy associated with the particle confined into an atom. The study of expectation value is very important because all the conclusions of quantum theory representing this value. Various physical properties can be deduced by selecting appropriate operator. We get different properties: position in space, position from the nucleus, momentum, kinetic energy, potential energy, total energy associated with particle. All various physical properties and its average value can be deduced by selecting proper operator and putting its value over here. We can get the average value or significance means for different physical property associated with the particle confined into an atom. Now, next theory, that is particle confined in one dimension box or particle in potential well. Well, this is the diagram we need to understand. This is the origin, x is equal to 0, where we put the nucleus, and from nucleus to x direction we select an arbitrary point, x is equal to L, and we restrict the movement of particle between this nucleus to this x is equal to L. In this volume of space, electrons movement is restricted. We have two large infinitely high wall. This is on x is equal to 0 and this another wall is on x is equal to L, and in this, between these two wall, we have a potential well. Inside this well, the value of potential energy is considered to be 0, and outside the well the potential energy is infinitely high. Even on the wall the potential energy would be infinitely high. When x is equal to 0, there should be a nucleus. So on this wall there is no probability of finding electron, and here x is equal to L. Here also the potential energy is infinitely high, so there is no probability of finding electron. That means the movement of electron is strictly restricted into the wall, not on the wall, into the well, right? So that you need to understand, and then we can start. Consider particle moving in one dimension box of length L. Here 0 x is equal to 0 to x is equal to L, that is length L. So that length L with infinitely high walls. This wall is infinitely high, that you need to understand. This wall also infinitely high, and it is infinitely high walls at two ends. Inside the box, the potential energy is considered to be 0. Here also written, inside the box potential energy is considered to be 0, and outside the box the potential energy is infinite. So here the value of potential energy is infinite, and even on this wall as well, the potential energy value would be infinite. In other words, the particle is confined to move in the length L. Here it can move. It cannot come on this wall, it cannot come on this wall, but it can freely move in this space. The model also called particle in a potential well. Here potential energy is considered to be zero, and therefore this volume of space where the electron movement is restricted, that portion looks as if it is a potential well. Now for this we have Schrödinger equation, d square psi by dx square plus 8 pi square m upon h square E minus v psi is equal to 0. In this Schrödinger equation, psi represents the wave function, that is probability of finding electron in this volume of space. X dx, that is the volume of space in which the electron is going to move. 8 pi square, that is a constant value. M is the mass of the particle. H square, that is Planck constant. E is the total energy, V is the potential energy, and the difference shows kinetic energy associated with particle. So Schrödinger equation gives all these different property associated with particle confined into this one dimension box. And you can see here in this figure, I will going to show you 1, 2, 3, 4, 5 and 6 positions are shown over here. You can see here there is big wavelength. Here the wavelength little decrease. Here the wavelength even decrease. Here wavelength even decrease and more decrease. So more the wavelength decrease, movement of particle get increase. That we can found in this one dimension box. You can see here. Since the potential is discontinuous, that means at some position low value, at very next position sudden rise. So that is called potential discontinuity. At x is equal to 0, that is one wall, and at x is equal to L, that is another wall. So on wall there is sudden rise in the potential value, because there the value of potential energy would be infinity. Inside the wall potential energy would be 0. So potential is discontinuous. A sudden rise at x is equal to 0 and x is equal to L. It is convenient to consider the Schrödinger equation inside and outside the box separately. So let us consider Schrödinger equation outside the box. In outside the box potential energy is infinity. So that can be represented as d square psi by dx square plus 8 pi square m upon s square E minus v. Instead we can put infinity symbol. Psi is equal to 0. So this is the Schrödinger equation associated with the particle outside the box. Schrödinger equation now we can get inside the box, and inside the box, that is between limit 0 to L, because that is the area only where the movement of the particle is restricted, and there the value of potential energy is considered to be 0. So the Schrödinger equation can be written as d square psi by dx square plus 8 pi square m upon s square E minus V, that is a potential energy and that is 0. So we put 0 here, psi is equal to 0. That means d square psi by dx square plus 8 pi square m upon s square E psi is equal to 0. This is the Schrödinger equation associated with the particle confined into one dimension box inside the box. Due to infinitely large potential energy beyond the boundary of the box, that is x is equal to 0 wall and x is equal to L wall, the particle has no chance of being found in a region where x is less than 0 or x is greater than L. That is why psi square and hence the psi is equal to 0 in this region. You know that x is equal to 0 where we put nucleus, and on nucleus there is no probability of finding electron, and that wall there is no particle can be observed as the potential energy is infinitely high. While on x is equal to L there is another wall, there also potential energy is infinitely high, so there is no probability of finding electron because of the discontinuity which already we have discussed earlier. Since psi must be continuous, it cannot rise or fall suddenly by large amount of energy, and therefore psi must be 0 on the wall x is equal to 0 and on the another wall x is equal to L. So on both the wall psi must be 0. That means there is no probability of finding particle on first wall, that is x is equal to 0, or on second wall, that is x is equal to L. This is called the boundary condition for the system. If somebody will ask you what is the boundary condition for one dimension box, so this is the boundary condition that on x is equal to 0 psi must be 0 and on x is equal to L psi must be 0, because it cannot rise or fall suddenly by large amount of energy, and on x is equal to 0 value of potential energy is infinitely high. Inside the box value of potential energy is 0, and on x is equal to L another wall value of potential energy is infinitely high. So on wall there is no probability of finding electron, therefore psi must be 0, and inside the box we can find the probability of finding particle, because particle is considered to be confined into one dimension box. This Schrodinger equation inside the box may be written as d square psi by dx square plus 8 pi square m upon h square E psi is equal to 0. Now if I keep this to this side of 0, we get d square psi by dx square is equal to this plus convert into minus 8 pi square m upon h square E psi. Now if for this bracket we abbreviated it as k square, then d square psi by dx square is equal to k square psi, where k is equal to 8 pi square m upon h square E. So if this I kept this side, I can write d square psi by dx square plus k square psi is equal to 0. This is equation number 3, and you need to remember this equation number 3. And this is also a Schrodinger equation like this one. In this equation and this equation we have done only one change, that is for this 8 pi square m upon h square E we have taken a symbol k square. That is the only difference, otherwise these two equations are quite similar. So k square is equal to 8 pi square m upon h square E. That is equation number 4 that you need to remember as well. Equation 3 is the same as equation 2, which is satisfied by any of the function like sine kx, cos kx, exponential ikx and exponential minus ikx, all of which are finite, single valued and continuous, that means normalized wave function, fulfilling the necessary criteria of an acceptable wave function. The wave function psi may be expressed in terms of exponential plus or minus ikx or in terms of sin kx and cos kx. Both the complex and the rate forms have their own advantages. In terms of the real form of the wave function, the general solution can be written as psi is equal to a sin kx plus b cos kx. That is equation number 5. Now you think how this value of psi will come. Psi has unlimited solution, but only this solution can be accepted as this solution gives finite single valued continuous value for this wave function. So those solutions which follow all those four conditions are considered to be accepted solution for the wave function. So we got this equation in that way, where a and b are the arbitrary constants, random constants introduced during the integration. The value of a, b and k are determined by the boundary conditions which already we have studied. What are the boundary conditions? X is equal to 0, there is no probability of finding electron, and X is equal to L, there is no probability of finding electron as well. So these are the two boundary conditions. X is equal to 0, psi is equal to 0, because on nucleus there is no probability of finding electron. Therefore, equation 5 can be written as 0 is equal to a sine k into 0, because x is equal to 0, b cos k into 0. So here x and x value should be 0, x value should be 0. So we get this equation 5 written in this form. Now sine 0, k into 0, that is sine 0, sine 0 is equal to 0, and k into 0, that is cos 0, and cos 0 is equal to 1. So we got the value for this 0, a into sine 0, that is 0, and b into cos 0, that is 1. So arbitrary constant b value we have obtained, and that is 0. Hence we can get the equation psi is equal to a sine kx plus b cos kx. Now substituting the value of arbitrary constant b here, we are going to get a sine kx plus 0 cos kx, because b is 0. Therefore psi is equal to a sine kx for all the value of x. Also at x is equal to L, another boundary condition, the wave function psi is equal to 0, because in this wall x is equal to L, the potential energy is infinitely high, and inside the box potential energy is 0. So sudden increase is not accepted. That means we can say that on x is equal to L wall there is no probability of finding electron. So that value is also 0. 0 is equal to a sine kl. Now instead of x we need to put L, plus now value of b is 0 cos kl. Therefore 0 is equal to a sine kl. This is equation number 6. Equation 6 is satisfied if either a is equal to 0, this arbitrary constant value should be 0, or kl is equal to n pi, because if we put n pi over here, sine n pi, that is 0 as well. So a sine kx is equal to 0. A can be 0 or either a sine n pi. Instead of kl I can put n pi. A sine n pi would be 0. However, both a and b can be 0. Psi will become 0 if we consider that both the arbitrary constant 0, that means psi must be 0, and that is not possible because we have confined one particle into box. That means particle is there, psi should not be 0 there. That means a cannot be 0. It means that sine n pi should be 0. So the other solution, kl is equal to n pi. So that n pi, when we are going to put it here, sine n pi, that is going to be 0. So that value would be right and acceptable value. Hence kl is equal to n pi. So k is equal to n pi by l, where n is a single integer and its value would be 1, 2, 3 up to infinity, but not 0, not negative. If n would be 0, definitely k would be 0 and the wave function again would be 0, which is not possible. There considerable lead to the solution that psi is equal to a sin kx plus b cos kx, where b is equal to 0 while k value would be n pi by l. Therefore, psi can be written as a sin n pi by lx. Now we have put the value of k over here, and from equation 4, k square would be 8 pi square m upon h square e. So that relation will gives the value of energy E, and that energy E is equal to this will going up and this will going down. So we're going to get k square h square upon 8 pi square m, and we will going to put the value of k now, that is n pi by l. So substituting the value of k over here, we're going to get n square pi square h square upon 8 pi square m l square. Now pi square will cancel out each other, and we're going to get the value of energy associated with the particle confined into one dimension box, and that total energy is n square h square upon 8 ml square. Now here the value of n, as already we have seen, is 1, 2, 3 up to infinite, but not 0, not negative. So if we'll put the minimum value for n, that is n is equal to 1, we're going to get the energy value E is equal to h square upon 8 ml square. This minimum energy is known as 0-point energy for particle confined into one dimension box. If somebody will ask you what is the 0-point energy for the particle confined into one dimension box, you need to put the value of n over here as 1. You get E is equal to h square upon 8 ml square. That is 0-point energy for a particle confined into one dimension box. Now next theory, that is particle in a ring. So here the nucleus is, and the arbitrary point is selected, that is x is equal to 0, from which electron is strictly restricted to move in this circular path, not in a wavy nature. It's strictly moved to move on this circular path of radius r, and when it completes this entire circumference, it reaches to the origin position again. But when it reaches to that position, the value would be x is equal to c. C stands for circumference. X, that is 0, starting point, and after completing the circumference, again the particle reached to the same point again, then that value would be x is equal to c. Now the story differ here, that is the two boundary condition. Here in the one dimension box, when x is equal to 0, there is nucleus, so there is no probability of finding electron. But here when x is equal to 0, it is away from the nucleus, so there is probability of finding electron. That means wave function should not be 0 there. And on x is equal to c is the same point, so there also there is probability of finding electron. That means size should not be 0. While in one dimension box, as x is equal to 0 and x is equal to l, on two wall infinitely high potential energy, and therefore there is no probability of finding electron. While here in the particle in a ring, x is equal to 0 and x is equal to c, in both the position there is probability of finding electron. Psi should not be 0. That is how these two theory differs from each other. A single particle executing a rotational motion, the Schrodinger equation can be solved exactly. The rotational motion crops up whenever we have to deal with motion of a particle under the influence of a central field of force, as for example the motion of an electron surrounding nucleus of an atom. This is another diagram. This is a nucleus, distance r, x arbitrary point, starting point, and electrons start moving and reach to the same point by completing the circumference. Suppose an electron of mass m is restricted to move along a circular track of radius r on which potential energy is considered to be constant. So on this path, potential energy value is constant. Outside and inside the path, the value of potential energy is considered to be infinitely high, and on the path, potential energy is considered to be zero, that is constant. So in order to solve this problem, the polar coordinates will be used instead of Cartesian coordinates. The one-dimensional Schrodinger equation can be written as d square psi by dx square plus 8 pi square m upon h square e minus v psi is equal to 0. Now here also we have two values as shown in the figure. An arbitrary point on the ring is chosen as origin point, that is x is equal to 0, and the coordinate x is varies round the circular track. So x value get changed at each of this point on the circle, and when it reaches to again the same point, it will complete the entire circumference of the circle. Let C be the length of the circumference of the ring. Since the wave function must be single valued, we have psi x is equal to psi x plus C. Setting the potential energy V equal to 0 and also x is equal to 0, d square psi by dx square plus 8 pi square m upon s square e. Now potential energy is considered to be 0 at the starting point. We're going to get this Schrodinger equation, and here for 8 pi square m upon s square e, if we're going to take k square, we're going to get this simple equation. Up to this, it is quite similar if we compare with one particle confined into one dimension box. D square psi by dx square plus k square psi is equal to 0. That is also a Schrodinger equation like this one. There is no difference. Only the difference is that instead of 8 pi square m upon s square e, we have taken k square. That is the only difference. And in one dimension box also, up to this, it is quite similar. The general solution for this equation is psi is equal to a sin kx plus b cos kx. That is also similar. Now where it is similar, where it differ, that I am going to explain you. Boundary condition. Here the story get differ. In the boundary condition for one dimension box, x is equal to 0 and x is equal to L, potential energy is infinitely high, where there is no probability of finding electron on the ball. While here the boundary conditions are now different from those of one dimension box. According to equation 2, when x is equal to 0, psi should not be 0, but it should be psi c, or you can put psi 2 pi. So in this equation 4, psi 0 is equal to a sin k0. Instead of x, we need to put 0. So k0 plus b cos k0. This is the starting point. Psi is equal to b. Now there b is equal to 0. Here b is equal to the wave function itself, psi. Because sin 0 is equal to 0 and cos 0 is equal to 1. So cos 0 is equal to 1, that is b. Sin k0, sin 0 is equal to 0. So 0 into a, that is 0. So b is equal to psi 0 and psi 0 is equal to psi c. That means b is equal to psi. That means here b value indicate the probability of finding electron. Now substituting the value psi is equal to b in this equation, we're going to get x is equal to c. So in equation 4 we get b is equal to a sin kc plus b cos kc. That is equation number 5. You need to remember this equation 5 as well. When there is no discontinuity in potential energy, in case both psi and d psi by dx, its single differentiation, must be continuous. Thus we have another condition, and that condition is psi d psi by dx x is equal to 0 should be equal to d psi by dx x is equal to c, because the starting point and ending point after the circumference is similar. These two also give similar. This is equation number 6. As psi is equal to a sin kx plus b cos kx from equation 4, left hand side of the equation will become d psi by dx, where x is equal to 0. So here instead of psi, we need to substitute this value. So if substituting the value of psi here, we are going to get d by dx a sin kx plus b cos kx, where x is equal to 0. Do not forget that. So d psi by dx, where x is equal to 0, is equal to ak. When you take the single differentiation of this equation, k constant remain outside and sine convert into cos. So d by dx of a sin kx written as ak cos kx, and d by dx of b cos kx can be written as cos converted into minus sine minus bk sin kx. Now taking x is equal to 0, we get d psi by dx, x is equal to 0. When we put 0 over here, cos 0 is equal to 1. So here cos 0 and sine k0 is equal to 0. So we're going to get d psi by dx, x is equal to 0 would be ak, because cos 0 is equal to 1. Sine 0 is equal to 0. 0 into bk, that is 0. So we got this value d psi by dx, where x is equal to 0, we get ak. Now the right hand side of equation 6 will become d psi by dx. Now instead of x is equal to 0, this time we have x is equal to c d by dx. Now we are substituting the value of wave function psi, that is a sin kx plus b cos kx. So d psi by dx, x is equal to c, ak is equal to, now sin will convert it into cos kc and cos kx will be converted into sin kc. So this is single differentiation operation done on this wave function. We're going to get this value where x is equal to c, which leads to ak is equal to ak cos kc minus bk sin kc. Multiplying equation 5 with bk and equation 7 with a, we're going to obtain b square k is equal to abk sin kc plus b square k is equal to cos kc. Sorry, b square k is equal to abk sin kc plus b square k cos kc. And sin equation 7, multiplying this equation with a, we're going to get a square k is equal to a square k cos kc minus abk sin kc. Adding these two equations, we're going to get a square k plus b square k, this is two addition, is equal to abk sin kc plus b square k cos kc plus a square k cos kc minus abk sin kc. Now this is minus abk sin kc and this is plus abk sin kc, so it will cancel out each other and we're going to get a square k plus b square k is equal to b square k cos kc plus a square k cos kc. Now from this equation, if we kept k common, k square common, sorry, k common, we're going to get a square plus b square is equal to k cos kc. When you kept common, a square plus b square. Now this k and a square plus b square, which is similar both the side, so that will cancel out each other. We're going to get cos kc is equal to 1. So kc is equal to, when you take cos inverse, you're going to get the value of kc, and that value of kc is equal to 2n pi, where n is equal to 0 plus or minus 1 plus or minus 2 up to infinite. Now here also value of n differ from that of the case of one dimension box, where the value of n would be 1, 2, 3, not 0, not negative. Here 0 is there as well, negative is there as well. So value of n differs here in the particle in the ring. So cos minus theta is equal to cos theta. That in the trigonometry relation we have used. Now according to equation 3, we're going to get E is equal to k square s square upon 8 pi square m from equation 8, and we get the value of k over here 2n pi by c. So substituting the value of k into this equation, we're going to get E is equal to 2n pi by c square into s square upon 8 pi square m. So that will going to gives us the value of energy E is equal to n square s square upon 2mc square. So this is the energy associated with the particle confined to move into a ring. And with that, our syllabus comes to an end. This is enough from my end. Thank you very much for listening me patiently, and keep asking question. As you know, asking question is a beautiful way of gaining knowledge. And I will like to read this quote for you as क्यों डरे जिंदगी में क्या होगा, हर वक्त क्यों सोचे कि बुरा ही बुरा होगा, बढ़ते रहे मंजिलों की ओर हम, कुछ भी न मिला तो क्या, तजुर्बा तो नया होगा. Good morning. Keep motivating yourself. Be positive. Thank you very much.